Okay, so number three is largely an exercise in logarithmic derivatives and algebra slash substitution. So we'll just go ahead and make our way through it. The stellar temperature gradient when radiative diffusion is the dominant energy transport mechanism is given by the following equation. We're actually not going to use that in part A, so we'll just skip ahead and read what part A is asking us to do. Show that the critical temperature gradient for convection is given by the following. Well, and this is just a good general piece of information to know. It's good to know what exactly is the criterion for what determines whether a certain zone in a star is going to be convective or radiative, and that is given by something called the Schwarzschild Criterion, and it looks like this. So nice and small and succinct. So whenever we have this little upside down triangle here, upside down delta, the little nabla, that is something that we usually refer to as the temperature gradient, but remember it's not the same thing as a dTdr type of temperature gradient. We call it a temperature gradient, but it is actually a logarithmic derivative of temperature with respect to pressure. So dlnt over dlnp, where ln is the natural logarithm, t is temperature, P is pressure, and whenever we're in a particular opaque part of the star, and the temperature gradient is too small, we will when this criterion is satisfied that I've written down is satisfied, then we get convection if nabla rad is smaller than nabla 80, then we are going to get radiative dominance. Okay, so how do we show the how do we get to the point where we're showing equation 12? Well, we should start off by expressing or separating the DL and T from DL and P by turning them to their own separate logarithms with respect to distance or radius or depth in the star. What I mean by that is basically just multiplying and dividing the top and bottom by dr. So we're going to get two drs in here. Oops, sorry, I have a lot of space up there. Undo. And these are both adiabatic. Okay, so just as an intermediate step, I want to separate, what we're taking the derivative of from the differential itself. So just separating the LNT and the LNP from the DDR. So we're thinking of this now as a derivative with respect to radius, but the function that we're taking the derivative on is the logarithms of the T and the P. These are both still assuming adiabatic. We know how to do that. Learn how to do that in calculus. And what we're left over with is 1 over x, 1 over what we had inside the logarithm, and then just a leftover dtdr over here. That is still adiabatic, and the bottom is going to look exactly the same, except we have pressure instead of temperature. Okay. Okay, so I have these 6 things that are all equal to each other. So the far left is then going to be equal to the far right. And by far left, I mean all the gamma stuff. So I want to keep the gammas. And I'm just going to copy what I have on the far right, but simplify it a little bit, move the P up to the top, and move the T down to the bottom. Yeah. Okay. These are still assuming adiabatic. And then I want to solve for dT/dr convective, basically. So let me just take what I have and then rearrange it so that I'm solving for the dT/dr that I have, and then show why, or then explain why adiabatic is the same thing as convective. So I'm isolating that, which means I'm keeping the gammas, but then rearranging the t's and the p's. All right, so this looks super similar to what they have written down on the page. So one minor thing is that they're using square brackets instead of round parentheses like I am. So again, the criterion for determining whether a certain region in a star is going to be convective or not depends on comparing the temperature gradient at that region to an adiabatic temperature gradient. So that's why the adiabatic and convective are the same, and I can just replace one for the other. Gamma is, of course, gamma, adiabatic index, temperature is just temperature, and then pressure is just pressure. And then there's further justification for this in the textbook, but just to make sure that my equation looks the same as theirs, we can actually just drop the adiabatic subscript on the pressure gradient, because the pressure gradient doesn't care about whether it's in a radiative or a convective dominated region. So those are indistinguishable from one another. So I can just drop the index. So this has been part A.